Like, you don't like my white title, you're welcome to change it as well. You change it to something that means something to you. That's what you should do. A lot of people, what they say is like figures. Figures are the most often ignored thing, but sometimes the most important thing in studying. When people read the chapter, oftentimes, and they did this study a while back ago, where a lot of people don't even bother reading the figure caption, and they don't really spend much time looking at the figures. Whereas in this particular study, they're saying that the amount of time the readers spent on the figures versus the importance of the figures was totally lopsided. In other words, they had it backwards. The reader should have been spending more time on the figures to understand the concepts than and so they have the priorities set differently. Not all figures are like that. A lot of the figures aren't that important. This figure is important, so this is why I spent a lot of time waiting for this particular one, because this is not the, this is maybe the fourth time you've seen it here, but this is not the last time you'll see this. This is an extremely important figure. And what does this figure tell us? This is an extremely important figure in science. And this one is used to get a lot of equations and laws that you end up using in science. Not necessarily in Chem 4, but later on in science. But this tells us this: at 25 degrees C. Say this is at 25 degrees C. At 25 degrees C, do all the water molecules have the exact same kinetic energy? I've asked this question before. If you have a sample of water at room temperature, does every single water molecule in that sample at 25 degrees C have the exact same kinetic energy? And the answer is no. Well, if they don't have the exact same kinetic energy, then what kinetic energies do they have? So this is a plot showing that 25 degrees C is a distribution of kinetic energies. So in this figure, what we see here is this. We have an energy cutoff here. This energy cutoff is the minimum amount of energy required to vaporize off the surface, because this is from chapter 15. But the energy required to vaporize off the surface is kind of low compared to the energy that's required to break bonds and form unstable molecules or unstable ions like hydronium and hydroxide. And therefore, this energy cutoff for the reaction, autoionization of water, is way up here. Meaning that if I had like 1 billion water molecules, about how many have enough energy to react? If I had 1 billion water molecules, about how many? If I had 1 billion water molecules, then quite a few have enough energy to react, like 10%, to vaporize off the surface. To vaporize off the surface, but to actually react, the energy cutoff is way higher. So this is the energy required for reaction, for auto reaction. Auto just means reacting with itself. Call it auto-ionization or auto-hydrolysis of water. The energy cutoff for vaporization is like around here. The energy required for auto reaction is way up here. So you might not have caught it, but they're about 4. About 4 out of 1 billion. So about 4 out of a billion, so a billion water molecules here, 4 of them react. Is that really worth worrying about? No, and therefore if we say no reaction, it's pretty accurate. I mean, there's really no reaction here. But it turns out that 4 out of a billion is important because if it weren't for that 4 out of a billion, you wouldn't have a pH of, the pH of water, 7. Actually, did I finish up, did I talk about pH on Thursday? Or did I skip that? The anti-log? How about this? Does this look familiar at all or not? So this is the reaction. If we take water, liquid plus water, liquid, and collides, it's going to form some hydronium and some hydroxide like this. That's the reaction. This is called water autoionization or water hydrolysis. Or just the acid-base reaction. If we just did this normally, like a normal stoichiometry problem, we'd say that there's no driving force, therefore we'd say that there's no reaction. But it turns out, just because the dynamics of this, there's a tiny, tiny bit of reaction. And that tiny, tiny bit of reaction is important because that's what leads to pH. pH is 7. So a little bit of reaction does occur. So this is the first, the water equilibrium was the first. This is reversible. Of course, this is reversible because the reverse reaction is so much more favored. And so, but what we can do is we can just ignore this tiny bit of product that forms here. Or if we want to worry about it, then we can worry about it. But how do we deal with it? Because here's the reactant, here's the product. And so if we want the stoichiometry of this, then how much forms, then we have to handle the stoichiometry differently. That's how much forms. We could wait and wait and wait. But what happens is no additional hydronium and hydroxide will build up. And so we'll have pH 7 and it stops. The reason is because at that point, the forward and the reverse reaction are equal. That is, we're forming this as quickly as it's being consumed, because this is a highly favorable reaction in the reverse direction. So, we go back to this slide, and so at the particular level we have collisions. So there's going to be a violent collision between the two water molecules. When we have collision, not all collisions are successful. One, we have to have enough kinetic energy. And so we see here, in terms of kinetic energy, most of the molecules don't have enough kinetic energy. There's going to be a certain minimum kinetic energy that's required for reaction, and that's shown here. And so just a tiny fraction of molecules, in the case of water, have enough kinetic energy. And so there's got to be enough kinetic. And then even if there's enough kinetic energy, there has to be a proper orientation. So the orientation, they have to collide with the oxygen colliding with the hydrogen. We can't have two hydrogens colliding, and we can't have two oxygens colliding because that won't lead to reaction. And so we need the proper orientation. You can see orientation here, though this is not for water. This is orientation for this blue and red. So if we have this blue diatomic molecule reacting with the red one, this is a successful collision. There's enough energy to break the bonds, and the orientation is correct. Here, this would be an unsuccessful collision here. Although that does look successful, then this isn't quite successful, and they end up bouncing off each other. And the same thing here. They aren't hitting it in the correct orientation. So they might have enough energy, but they just don't have the right orientation. Here. And so we need two things for a collision to be successful. And so that means that most of these collisions aren't going to react. Whereas hydronium and hydroxide, that can easily be successful here, going backwards, back to water. Okay, one thing that we don't see when these collide is this bond breakage and bond formation process. What's happening in the transition between product and reactant. So normally when we think, okay, nothing's happening, it's just going from reactants to products. But when we look at it in more detail, when we want to see, what and how the bonds are breaking and how are the bonds forming. And so that's what we call a transition state. So what is happening here? There's some transition state. The transition state we don't actually see like this or write down. And so here we're going from two waters to a hydronium and hydroxide. Well, it just doesn't go there easily in one step like this. And so from this side, we're just looking at the transition state here. We're going to be looking at the energetics of this in more detail, but you can ignore this, delta E. The delta E is just the gap show in the energy. This potential energy barrier, I'm not going to talk about that, but the activation energy, I will talk about that, the activation energy. Well, let's take a look at this figure here first. And if you look at this figure here, what would you call this figure? Name this. Is there a title for this figure?
Reaction progress graph.
What's that? You call it reaction progress? It is called. This is a reaction progress figure. Well, they called it the transition state complex reaction progress. Maybe, I don't know. They didn't name this. That's a problem. This is called a reaction profile or reaction progress. And so here, we start off with the reactants. So we'll just label this the reactants. The reactants are going to have some energy. So on the y-axis is lot energy. We don't have numbers here, it's just relative. And so we start off here, and then we go to products. The products are going to be lower in energy. So that's like this. It's downhill, right? It should be downhill all the way. But in order to go from reactants to products, even though it's downhill, there's a barrier here, an energy barrier. And why is there an energy barrier here? There's an energy barrier because of collisions. Collisions have to have enough energy to break the bonds here and start forming new bonds here. And so initially we have to have a collision, and that collision has to be violent enough. When we form the products in full, then we should get that energy back because the products are more stable. But in the transition in going from reactants to products, we do have to deal with this energy barrier. This energy barrier is called a potential energy barrier or an activation energy. And so we call it the E sub A, which stands for activation energy. So here, this is something we don't see. Here the reactants are coming together. So we see the reactants and we see the products. Well, how did it get from the reactants to the products? How it got from the reactants to the products is there must have been a collision. This collision must have had enough energy to start breaking the bonds. So these bonds are starting to break here. And we're also starting to form bonds. And so this is just a snapshot, of the way bonds are breaking, bonds are breaking, bonds are breaking. Take a snapshot here. Bonds have broken, new bonds have formed. And so right in the middle here, P, this is a snapshot of the reaction. Now, the transition state complex is something that you don't isolate, you don't track, and you don't see. It's just something that occurred along the way, and it's going to cost us energy here. And so, a perfect example of this particular reaction is this. Methane and oxygen. And so we have to look at it in more detail here. If you look at methane and oxygen, that's a high energy mixture or high potential energy mixture compared to CO2 and water. CO2 and water is a much more stable mixture than methane and oxygen. And so this should just be a downhill reaction to CO2 and water. But what happens is if I mix methane with oxygen in the air, do you see any reaction occurring? No, even though there's a big driving force for this reaction, the big driving force is going from stronger reducer, stronger oxidizer, weaker oxidizer, weaker reducer. And so there should just be a straight downhill. The problem is in order to get these to react, there has to be a collision. And so there's going to be a big collision here, or more than one collision. But essentially, there has to be a collision with enough energy to start the bonds breaking and start the bonds forming. And once you completely form the new bonds, then it's going to be overall more stable. But in getting from this less stable to the more stable, we had to get through an even less stable transition state or transition states. There could be multiple humps in this. I'm only drawing one hump because I don't want to get into too much detail, but there could be multiple humps to it. And so, what fraction of molecules has enough energy at room temperature? At room temperature, do you see much combustion going on? No. So at room temperature, the fraction of molecules with sufficient kinetic energy, so we're going to replace this now. Rather than having this as water, this is going to be at room temperature. This is going to be methane and O2. At room temperature, what fraction? Well, it's a small fraction because I don't see much combustion happening. And therefore, the bulk of the molecules are kind of trapped here. They're trapped here. Even though they want to react here, there just aren't enough molecules that have enough energy to go over this hump. A few do. Of course, a few do. And so there's reaction occurring, but you can't see it because it's happening so slowly and so little reactions happening. But what we can also do is we can change the distribution. So for example, this, even though at 25 degrees C, the methanes and the oxygens are going to have a distribution of kinetic energies, their average is going to correspond to the temperature. So if I increase the temperature, that's going to increase the average kinetic energy. And so if that increases the average kinetic energy, which is around here, to higher, that's going to shift the whole distribution to higher energy. And so at 25 degrees C, we see a distribution like this. At higher temperature, what's going to happen is the lower energy population is going to shrink, and the higher energy population is going to grow. So this will be at a T greater than 25 degrees C. So at higher temperatures, the population that has enough energy to react grows. And so if there's more that have enough energy to react, then we should see some combustion happening. And so one way to increase the temperatures is by match or hot surface. We don't need a match, just a hot surface would do. here. I have my methane, oxygen. If I lower the temperature, then that's going to make the reaction even slower, because if I lower the temperature, what that's going to do is it's going to shift the average down to lower temperature, which is going to increase the, should I take different colors for this? But it's going to increase the lower kinetic energy and decrease the higher kinetic energy population. And so this is a T greater than, lower than 25. You see. So the question comes up then, don't I have to continually hold the match to the mixture in order to have the reaction occur? So if I remove the match here, the reaction is self-sustaining. So why is that self-sustaining? Well, the reason is because you need the initial pioneers that you help with the match. And so you help some of the molecules react. Well, once they've gone over the hump here, and in other words, once they've gone over the activation barrier, or activation energy here, they're going to make these stable products. When they make these stable products, that releases a huge amount of energy here. And so this drop in energy here to here is going to sustain the followers. And so we just need to get the pioneers over, and then there's enough energy to sustain the reaction here. So we don't continually have to heat it. The reaction's being heated by itself. All right, so this is just showing going over the hump. This is a slide showing kinetic versus potential energy. That one we're going to skip right now. But essentially what it means is the two molecules are colliding, and when they're colliding, they're moving quickly. And at the time of impact, they're moving slowly, because all that energy is being converted into kinetic energy, motion, into potential, breaking bonds. That's what's happening. Breaking bonds. So what I was just talking about with methane and oxygen is a thing about rate, the rate of reaction, because at room temperature, the reaction between methane and oxygen is very slow. At elevated temperature, it goes much faster. And so the rate is just based on population. The greater the population, the more collisions with enough energy. The more collisions with enough energy, the faster the reaction is going to occur. And so temperature is going to have a big and profound effect on rates of reaction. Higher temperature means faster reactions, greater population. Lower temperature means smaller population. Note, though, that the activation energy doesn't change. The activation energy is fixed. We're just manipulating the population here. So here's the slide again, with a different perspective. What do you call this graph? What do you name it? Well, since Craig Leachy didn't name it, we might as well name it ourselves. One thing that people do with plots is they name it y versus x. You could do the same thing. You could name it that. That's pretty descriptive. Y versus x. What is y? Number of molecules that have a particular energy. Well, that's different from the y he used before. What was the y he used before? The y he used before, does anybody recall? Yeah, percentage, it doesn't matter. Number, percentage, it doesn't matter. What it is it's the What it is the population distribution. In other words, what is this? This is the kinetic energy distribution or the population distribution or whatever you want to call it. It's fine. And what it should mean is it just means that at a given temperature, not everything has the same energy. There's going to be distribution of energies present. That distribution of energies is going to be impacted by temperature. How is it impacted by temperature? Well, higher temperatures. It's wrong. It's that figure again. You jumped too far ahead. At higher temperatures, what happened to the population? Well, at higher temperatures, the average kinetic energy shifted up, which means the whole population shifts up. At lower temperatures, the energy shifts down, the population shifts down. So what's happening with this? And so we can see at higher temperatures, we expect reactions to happen faster because the population with enough energy. Now, what is enough energy in this case? Enough energy, this is the minimum energy required for a reaction. It's here. What was the energy before? Let's solve it. The energy that we saw before is this one. What did he call this one? This energy is the energy to evaporate. The energy to evaporate is not nearly as high. The energy to evaporate is way lower than the amount required for reaction, because for reaction we have to break bonds. To evaporate, you just have to break the intermolecular forces that hold the molecules together in a liquid. So, a bit different in terms of energy. Actually, this is not the first time we saw it. You guys remember the first time we saw this graph? What chapter that was? What was the gas chapter? What was the first gas chapter that we saw? Actually, I'm not going to bother. Oh, the first time we saw it was like, it was the same thing. It was like population versus speed, not kinetic energy, but speed and kinetic energy are pretty much the same thing. So. But this is a very important graph. It's also called the Maxwell-Boltzmann distribution, or the thermal distribution. So a lot of people just call it the thermal distribution. You see it at a given temperature. So let's move on here. And so the point is that at a higher temperature, we expect more reaction. The reaction should happen faster. There are other things, that does not change the activation energy. This activation energy is minimum energy. If we had weak bonds would change it, because weak bonds we don't need as much energy to break. Strong bonds shifts it higher, weak bonds shifts it lower. But we don't have a choice of bonds because we got the reactants and that's what we want to react. But that didn't stop people from trying to manipulate this. Some people try to manipulate this activation energy because they want certain reactions to happen faster. And the way they manipulate it is by using catalysts. A catalyst, the sole function of the catalyst is to lower the activation energy to make the reaction easier, and therefore faster to occur. And so what do catalysts do? Well, catalysts, they do this, they lower the activation energy. So if we have a smaller hill to climb, then more molecules can make it over the hill. So the job of the catalyst is to lower the activation energy. If you lower the activation energy, well, that's going to increase the population. And so with a catalyst, the barrier drops here. making molecules with lower kinetic energy able to pass over the potential energy barrier. The potential energy barrier is just the hill. The taller the hill, the higher the potential energy. The potential energy barrier in this case is called the activation energy. The potential energy barrier and the activation energy are the same exact thing. And so, dealing with catalysts. Inhibitors screw up catalysts. And so here you can see, here's the activation barrier without catalyst. This is red, here's the activation barrier with a catalyst. And so how exactly does the catalyst work? Lowering it. Well, that's a question we need to answer. And so here's the activation energy without catalyst. Here's the activation energy with the catalyst. So we got a lot more of the population able to react. So we're going to have a lot more reaction. In other words, it will occur a lot faster.
What are examples of catalysts?
What are some examples of catalysts? A couple of examples of catalysts here. Let me just show you. One example of a catalyst are enzymes. Enzymes are biological catalysts. And so what they're going to do is they're just going to facilitate the reaction. So for example, if we're trying to form a bond here, this will be the catalyst here. And the catalyst facilitates bond formation. So let's form a bond between these two pieces here. So one links here, the other links here, and then we can facilitate the bond formation. It comes off. The reverse process is also catalyzed. So enzymes can catalyze bond breakage, that is, make it easier to break bonds. So typically this is what's shown. Let's say we want to break the bond here. Well, an enzyme can help that by first, there are going to be intermolecular attractions that draw the molecule in. And once they draw the molecule in, then these intermolecular attractions will put a tensile force on this spread. You know, so the enzyme is going to be pulling on the molecule from both sides. So it's pulling from the left and pulling from the right. It's going to weaken this bond. If this bond becomes weakened, then it's easier to break. We don't need as much energy to break it. It's a lot more molecules at 25 degrees C or whatever. Enzymes don't probably operate at higher temperatures than 25. Will break. And so the reverse process is catalyzed with a different catalyst. And this one looks like it's facilitating bond formation. Other catalysts are facilitating bond breakage. That's an enzyme. The enzyme's drawn as a cartoon like this because the molecules are big. So it's hard to see.
Yeast. Is yeast an enzyme? Yeast.
Is yeast an enzyme? Is yeast an enzyme? Anybody know? I've used yeast before. But I don't know, actually. I don't know. You know, enzymes, they usually, for biological enzymes, they usually change the name. To this. You know, the enzymes typically have an ase ending to it. Like invertase, protease, sucrase, etc. It doesn't seem like yeast themselves are enzymes, because enzymes just have one specific function. But it looks as if yeast relies on enzymes to carry out its biological.
Yeast is a fungus.
Okay, yeast is a fungus, so it's some kind of organ. The enzyme itself is not a living. The enzyme itself can be a molecule like that shown, or it could be this. Let me show you. another enzyme catalyzed reaction. Well, here's a shot of an enzyme. So the molecules kind of get quite big, so they represent, the bonds as ribbons, and sheets, and this kind of stuff, depending on the structure and how it folds on itself. So you can see it here. This is just a molecule. Big one, but just a molecule. And then your reactant molecules interact with it by intermolecular forces. But what we can see is some things can be quite simple. Look at my enzyme. Sucrase.
Is that like sugar is like sugar?
Yeah, sugars are sugars. In order to digest sugar, you have to break a bond. You have to hydrolyze a bond with sugar because, like, if you look at sucrose actually consists of two sugars, glucose and fructose. In order to start metabolizing the sucrose, you have to break apart the glucose from the fructose. If you were to break apart the glucose from the fructose, then under normal conditions it takes hours. So if you were to eat some sugar, it would take hours to digest it, hours. But you wouldn't get an instant, sugar rush. The reason you get an instant sugar rush is because of enzymes that speed up the reaction. And that particular enzyme helps break the bond, not form the bond. So you need to break the bond between glucose and fructose to start digesting the sugar. But let me show you. It doesn't have to be an enzyme. It would be like acid. So let me show you a figure. Unfortunately, I closed it. So, let's see. It doesn't have to be an enzyme. It could be something as simple as an acid, like a strong acid, like HCl. And so this is an organic chemistry reaction here. A lot of these you're looking at kind of Lewis acid-base type interactions to talk about. But here's a reaction that's happening without a catalyst. This is kind of the steps it goes through. But if we add some acid, what happens is the reaction can take a different path, a different what we call mechanism. If it can find a lower energy path, that's going to lower the activation barrier. It might be, a longer path, but as long as it's lower in energy, it's going to happen faster. And so by adding acid into this, then that helps facilitate the reaction by offering an alternate path for reaction. Alternate path would make, because these are the formal charges. The formal charges here are a lot less stable than the formal charges up here. So this turns out to be a lower energy path versus this one. This is important in organic chemistry, is looking at the formal charges and comparing different sets of formal charges and that type of stuff. The interesting thing is, at the end of the reaction, we regenerate the catalyst. So the catalyst is consumed in the first step and then spit out before the last step here. It's minus HX, so we can reuse the catalyst over and over again. Same thing with enzymes. They're reusable. Once it spits out the product, it can bind to new reactant molecules. That's a characteristic of all catalysts. They're consumed at the beginning and then regenerated at the end. And so this is an acid catalyzed pathway, much faster. If we look at, in fact, since you're interested, sucrase, which is uncatalyzed. So this is the reaction that you want to happen. You got sucrose here. Sucrose is called a disaccharide because it's made up of two sugars, glucose and fructose. We've got to hydrolyze this bond here. Now, acid catalyzed hydrolysis of this is way faster. This one takes less than a second compared to ours. Uncatalyzed reaction. Let's see. We have figures for that. Acid helps as well, hydrolysis a bit, but enzymes are much faster. And so, you could look that up, if you're interested in that. Our book doesn't really get into the reasons, so we aren't going to really get into the reasons either. It just provides a way, and the way is, there are lots of different ways. Catalytic converters and cars work a different way. But all of them do the same thing. All of them provide an alternate mechanism, an alternate pathway that costs less energy. It might be longer, but it costs less energy. And since it costs less energy, it's going to be faster. The long way is faster. Or it might be shorter. It depends on the mechanism itself. All right, there are other things that we can do to increase. So temperature is one way of increasing. Another way is concentration. So for example, if it's highly concentrated, it will happen faster. Because highly concentrated, you just got more molecules. If you got more molecules, you're going to naturally have a greater population and you'll have faster reaction. Okay, so that's what we're talking about in this. We're going to come back to the concentration as well. And so concentrated will just increase the total population of this. If we increase the total population, obviously this population is going to increase too. Here, these three figures show the same population. So if we had just 1 billion molecules, let's say, we're going to shift them to higher energy or shift them to lower energy based on temperature. Obviously, if we decrease the population, make things less concentrated, it's going to slow things down. Increasing population will speed things up. So this effect of concentration there. All right, we're going to talk about the equilibrium here. And look about latest principle. Next. So up to now, we've been talking about kinetics, the speed of the reaction. Now we're going to shift back over to thermodynamics. At the beginning, we were talking about thermodynamics. Thermodynamics, doesn't care about how fast or how long it takes. What it cares about is where it ends up. So if I have a tub like this and I fill it with 50 gallons of water on the right side or the left side, it doesn't matter. Let's pick the left side. Sorry. If I put 50 gallons of water on the left side, kinetics is concerned with how fast it's going to take to form the product. Thermodynamics doesn't. Thermodynamics cares about the balance between reactant and product. here, the balance, I don't care how long it takes to fill this tub. We could be filling this tub one drop at a time, it's gonna take a long time. Or we could dump all 50 gallons at once, it's gonna take a short time. So kinetics cares about that. Thermodynamics doesn't. Thermodynamics only cares about what's the balance going to be at the end. When you look at the balance here, is it mostly reactant or is it mostly product? Well, it's mostly reactant. Most of the water stays as reactant. Not much water shifts over to the product. And that means the reactants are more stable. So thermodynamics cares about stability. Okay, whereas kinetics would ask a question like this, well, how long did it take for the 50 gallons to reach what we call equilibrium? To reach the same level? Well, it depends, how much water. How concentrated? What's the temperature? Those types of things. Is there a catalyst or no catalyst? But for thermo, we don't answer questions like how long it takes. How long does it take to digest that sugar? Kinetics? What's favored? The digestion products or the original sugar? That's thermodynamics. And so what we're looking now, we're going back to thermodynamics, and that's Le Chatelier's principle. Now we've established that the levels are equal and we've reached the state of dynamic equilibrium. It's equilibrium because the water levels don't change. The water levels are the same, so we have a fixed amount of product and a fixed amount of reaction, and it's done. I mean, there's no further change that can take place. We don't expect any more reaction. This is what we call partial reaction. So this is what I call partial reaction. I don't think your book calls it partial reaction, but I call it partial reaction just because of we can't use standard stoichiometry. In standard stoichiometry, we either have 100% reaction or 0% reaction. And then we can use stoichiometry to do this. But when we have partial reaction like this, we got some product formed with some reactant left over, this kind of stuff. And then we have to use an alternate method. An alternate method, I haven't talked about that yet, but I'm going to talk about it pretty soon. Well, this is dynamic equilibrium. An equilibrium because no matter how much longer we wait, the water levels aren't going to change. The water levels reach the final state. And so all the water hasn't been converted into product. There's still a lot of water left over. That's in this scenario. Sometimes it favors a product. And you might wait and wait, but there's a little bit of reactant left over, and you're going to say, okay, I'm going to wait for that little bit of reactant to completely react. But when the water's at a level like this, is that reactant going to completely react? No. No matter what you do, no matter how long you wait, that's kinetic, no matter how long, the reaction's done. So we got our reactants, we got our product. And that means not all the reactant reacted. But this is heavily favoring product over here. And so this is also dynamic equilibrium. There's no change in the levels, but it's what we call an equilibrium. There should be no change. But dynamic means there's change. Dynamic means there's motion. And at the particular level there is change because water is moving left and right. We can't stop the waters from moving. And the same thing with this. Let me go back to chapter 17 a moment. The same thing with this reaction here. No matter how long we wait, not all the water molecules are going to react to form hydronium hydroxide. We could wait and wait and wait. Likewise, we could wait and wait, and all the hydronium and hydroxide should react. Right? All the hydronium and hydroxide should react to revert back to water because water is much more stable. But no matter how long we wait, not all of it's going to react. And the reason is because we can't stop the collisions. The collisions are going to happen. And once we reach the state of dynamic equilibrium, the collisions leading to product, the rate of the collisions leading to product is equal to the rate of the collisions leading to reactant. This is what happens that this collision is much more favorable. This collision being much more favorable, we don't need much in the way of concentration. Over here, we need high concentration to generate we need 1 billion water molecules. Over here, we don't need that much because this is a very low energy barrier. So this can react quite easily to work those back. And so this is going to be a difference. You don't need 1 billion versus 1 billion. You have 1 billion versus just a few. They're going to be equal. This few is so reactive. So we've hit the state of dynamic equilibrium. Now this is a closed system. A closed system means that we don't add anything or remove anything. But Le Chatelier's does not deal with closed systems. Le Chatelier's deals with a system that is no longer closed like this. This would be a closed system. Le Chatelier says, okay, we have 50 gallons here. What if I add one more gallon? Well, in a closed system, you're not supposed to add one more gallon. The closed system is going to be 50 gallons, so that's it. And so in a sense, this is an open system. Now, it depends on where you add the 1 gallon. What if I add 1 gallon to the reactant side here? What do you think is going to happen? If I add 1 gallon of additional water to the left side, then is this still going to be at equilibrium? No, because what's going to happen is the left side is going to be at a higher level than the right side. And so if the left side goes at a higher level, what's going to happen? Well, water is going to shift. Water has to shift to the right so that the two levels can equilibrate again. And so if I add water to the left side, then the water is going to shift to the right so that the two levels are the same again. How long that takes is kinetics, but we're ignoring kinetics now. What we want to know is just what happens. And so we call that a shift right. What if I add the 1 gallon to the right side, to the products? If I add the 1 gallon to the product side, then it's going to shift to the left until we reach equilibrium again. What if I remove water? If I start removing water out of the product side, what's going to happen? There's going to be a shift of water to the... Well, if I start removing water from here, the water is going to shift over here to compensate for it to try to achieve the same level. Or it goes dry. I mean, I could suck all the water out of this side and it'll shift all to the right. What if I remove reactant? If I remove reactant, it's going to shift left. And so this is all we're doing with Le Chatelier's principle. With Le Chatelier's, we're going to take a system that's already at an equilibrium. So we waited and we waited and we waited. This is the waiting process here. The waiting process is this. This is water shifting to the right. And so I put in all 50 gallons on the right side. And so I have all 50 gallons. Some water is going to shift to the right side. This is the rate. Well, once the water shifts to the right side, okay, this is kind of a weird scale. Once the water shifts to the right side, then some water can shift back left. And so as I build up the water on the right side, the water is shifting back left, and eventually I'm going to hit this point. This point here, if I've waited long enough, I hit the state of dynamic equilibrium, where the water is shifting both ways with equal speed or equal rates. That's the dynamic part. How long that takes is kinetic. Well, we don't care how long. We just know it's at equilibrium. So once we've established equilibrium, there's going to be no further net change. Now we're going to take this closed system and open it up. We're going to start adding things and removing things and see what happens. That's Le Chatelier's principle. Basically, when an equilibrium is disturbed, the equilibrium will shift in the direction that tries to return the substance disturbed to its original. It can't go back to its original condition because here, if I add 1 gallon, now I'm going to have a total of 51 gallons. And so that means both sides are going to increase. It can't go back to its original. But what it can do is it can go back to a balanced state. That is, the ratio has to be in the same ratio. Okay, I'm going to skip this slide here. So here's an example of a reversible. When you see this, then you got to worry. There's going to be partial reaction. Both forward and reverse reactions can happen. If we increase the H2S concentration, this is a concentration effect. So if we increase the H2S concentration, that's like pouring more water onto the reactant side. If we pour more water into the reactant side, that's going to shift the reaction to the right. Yeah. So that's like this. Increasing the reactant concentration is going to shift this to the right. What if we increase the hydrogen concentration? If we increase the hydrogen ion concentration, that's like adding more water to the right side. That should shift it to the left. And so that's the way I'd answer it. Increasing H2S results in a shift right. We're going to form more product. Decrease the reactants. Increasing hydrogen is going to shift it to the left. Decrease the product, increase the reactants. So this is how Carglici says, increase H2S, forward. In other words, forward reaction occurs. It shifts to the right. Increase the hydrogen, the reverse, shifts left, consuming some of the added H2 to return to a more balanced state. So shift right, shift left. Really what's said. Pressure does the same thing. Now, pressure and concentration are related. And so let's talk about Le Chatelier's in terms of pressure, well, concentration, pressure. Okay, increasing the reactant concentration. I'll just write R for reactants, is going to result in a shift right. Decreasing the reactant concentration results in a shift left. Increasing the product concentration shifts left. Decreasing the product concentration shifts right. You've got to make more product to compensate. Pressure. Increasing the pressure of the reactants will shift right. Decreasing the pressure of the reactants will shift left. Increasing the pressure of the products, shift left. Decreasing the pressure of the products, shifts right. You know, the higher the pressure, one way of thinking about it is the greater the concentration at a given temperature. You think volume is the same, but volume is a bit more tricky. Increasing volume is both. You know, you're increasing the volume for both reactants and products, as if they're in the same container. So let's say we double the volume. Well, you just double the volume for both the reactants and the products. So what impact does that have? So increasing the volume shifts, well, we can't predict the shift ahead of time unless we know the reaction. And so increasing volume, what we say is this favors the side with larger volume. If both sides have the same volume, then there's no shift. Are of equal volume, then no shift. If I decrease the volume, you know, decreasing the volume favors the side with smaller volume. So if we have a equilibrium like this, again, we have this partial reaction. Eventually we're going to reach a state where there's going to be some kind of balance between reactants and products. I don't know if it's product favored or reactant favored or it's about equal, but it's not lopsided, you know, all products or all reactants. It's not lopsided, but some balance between the two. And so this has already reached equilibrium. In other words, we've given this long enough time, there's no more reaction that's going to take place. It's reached some kind of equilibrium or balance between reactants and products. I don't know what that balance is. It's reached some kind of balance. But if we're going to change the volume, it's going to screw up the balance. Why is it going to screw up the balance? Well, it might not screw up the balance. We have to look at the reaction. And then we look. For example, here we have 2 moles of H2O gas. You know, how much does a mole of H2O weigh? A mole of H2O weighs 18 grams. So 2 moles is 36 grams. If that were liquid, you know, how many milliliters would 36 grams of water occupy? 36 milliliters, good. So if this were 2 moles of H2O liquid, that's 36 milliliters of volume. But it's not 2 moles of H2O liquid, it's 2 moles of H2O gas. What's a molar volume of gas, roughly, under our current conditions? Ballpark. Just give me a ballpark number. 1 mole of gas occupies how many liters, roughly? Not at 0 degrees C, but more at room temperature. I don't know what pressure is today, but we'll just say it's around 1 atmosphere or 1 bar. Do you know how many liters a mole of gas occupies? Maybe not, because I told you I memorized that worthless number for me, which was at STP, but I gave you an alternate one to memorize, which was more useful. A lot more useful. Especially for Chem 1B, not necessarily for Chem 1A, although you see it in Chem 1A. 22.4 is at STP. This is 0 degrees C. It's too cold. I want it at 25 degrees C. It's bigger. We'll just say, okay, it's about, what is it, 24.79? Okay, we'll just call it 25. And so 2 moles of H2O gas is about, well, 25 liters per mole. That's 2 moles, that's 50 liters. Or 50,000 milliliters. And so if this were H2O liquid, it would occupy 36 milliliters. If I take the same 36 grams of water and make that a gas, it would occupy 50,000 milliliters. So we go from 36 milliliters to 50,000 milliliters. That's a pretty big volume. And so we got 50 liters here. About how much is 1 mole of gas then? About 25 liters. And so 25 plus 50 gives us 75 liters. So the reactants are about 75 liters. What are the products? Well, I have SiO2 solid. A mole of SiO2 solid, well, solids are typically more dense than liquids or less dense? Solids are typically more dense than liquids, and so this has got to have a pretty small volume. Compared to this, 4 moles of HF gas. 4 moles of gas is going to have about how many liters? 100. And so ignoring the solids, we typically ignore solids and liquids because the volumes are pretty small. Molar volumes are really small. We just stick with the gases. So over here we have 75, over here we have 100. Now we're going to reduce the volume. So if we squeeze this down, this reaction down, this equilibrium down, is it going to favor one side or the other? Yeah, if you squeeze this down, it's going to shift to make smaller volume, right? This is going to start feeling the pressure. And so you're squeezing this down, then we're going to have this reverse reaction occur, which makes 75 liters versus 100 liters. And so in other words, reducing the volume favors the smaller side, which is the left. And so we expect to shift left in this particular reaction here. And so decreasing volume favors the side with the smaller volume. And so to make a long story short, the shift is in the reverse direction because the reactants have a smaller volume than the products. What if both sides were the same? You know, one side has 100 liters, the other side has 100 liters. Then increasing or decreasing volume has no impact. There's no shift.
They reach equilibrium.
Yeah, and squeezing it or expanding it doesn't favor one side or the other. Over here, if I expand it, the volume, I'm expanding the volume, it's going to favor the right side because the right side needs more room. Therefore, it's going to shift forward. Here, Kakalici just says the molecules change from 4 to 3. This is for gases, you know, the moles, the coefficient. The moles of gas change from 4 to 3. Okay, we'll do one more, the temperature effect. When we do the temperature effect, we got to look, you know, at the reactions individually, just like volume. So for concentrations and pressures, we don't need to look at it. It's going to have a definite shift one way or the other because we're changing the reactants or the products. Here, for volume, it's a bit more tricky. We've got to look at it individually, and the same thing for temperature. You know, sometimes increasing temperature shifts it right, sometimes it shifts it left. Increasing temperature and decreasing temperature is a little bit more complicated than what I'm going to give you here. I don't want to get into it. You'll get into it in Chem 1B. We're just going to look at it very simplistically. And that is, if it's an endothermic reaction, think of an endothermic reaction. Well, I'll give you one. Melting ice is endothermic. So if I take ice and add heat to this, then I'm going to get water. So, what do you think? Increasing temperature here will shift this to the left or to the right? Well, if I increase the temperature, I'm adding heat. If I add heat, I'm adding reactant. If I add reactant, it should shift it to the, shift right. Let me put shift in quotation marks because this is a bit more complicated than that. If I decrease, that is, if I remove heat, you know, it shifts to the left. So it's going to make more ice. The shift is to the left. So in other words, if I want to melt ice, I better add heat. If I want to freeze water, I better remove heat. And then I can shift this both ways because this is reversible. This can go either way. That's for endothermic. For exothermic reactions, it's the opposite because exothermic reactions, heat is a product. And so let me give you an example of an exothermic. Water is converted to ice and heat. And so if I increase the temperature, which way will it shift? So if I increase the temperature, I'm adding heat. If I add heat, it's got to shift to the, so I'm adding product. So as I add more and more water or product, let's say product, as I add more heat, it's going to shift it left. So the shift is to the left. Okay, if I decrease the temperature, that is, if I remove heat, it should shift it to the right and make more ice. Shift right. And so for heat or temperature, it's a little bit more tricky because we've got to look at reaction by reaction. And so is this reaction here exothermic or endothermic? This is exothermic. Heat is being evolved as a product. And so at high temperatures, we're adding heat, so what does that do? Is it shift left or shift to the right? At high temperatures it's going to shift left, so we expect more NO2. The NO2s are shown here. So there's more NO2s, fewer N2O4s. If I cool it down, and so I decrease the temperature, I remove heat. You've got to decrease the temperature, remove heat. If you remove heat, it shifts to the right. If it shifts to the right, it makes more N2O4s. You can see a lot more N2O4s, very few NO2s. See, so we can shift it one way or the other, depending on if it's exothermic or endothermic with temperature. Okay, predict the direction this equilibrium will shift if the temperature is reduced. So we lower the temperature, which way is it going to go? Left or right? Okay, if it goes left, then we're going reverse, right? So if we decrease the temperature, does it shift left or reverse? And it shifts left. And a whole bunch of other stuff that we don't have to care about. Okay, that's Le Chatelier's principle. What I'll do is I'm going to stop at Le Chatelier's and then we'll talk about this next. So Le Chatelier's is just predicting the shift. You know, is it going to shift left or